Hi, in this video, we are going to look at a very interesting problem. It is about polynomials and basically Newton's symmetric sum identities. And we'll look at how we prove this. So let's go through the question. Let A, B, C be real numbers such that A plus B plus C is equal to 0. Prove that A power 5 plus B power 5 plus C power 5 by 5 is equal to A cube plus B cube plus C cube by 3 multiplied by A square plus B square plus C square by 2. Okay, so when we see this problem, the first thing that we can think of is, since A, B, and C are related in this way, we can think of A, B, and C as being the roots of a polynomial, as being the roots of a polynomial P of x is equal to 0. Obviously, this polynomial will be a cubic polynomial. And by Vieta's relation, we can write a cubic polynomial whose roots will be a, b, and c. So the way we'll do it is x cube plus ax minus b equal to 0, where a stands for ab plus bc plus ca and b stands for abc. Now, how am I getting this? I know that the sum of the roots, by Vieta's relation, we know a plus b plus c is equal to 0. If a, b, c are the roots, a plus b plus c is 0. That is given in the problem. Therefore, the coefficient of x square in this cubic must be 0, right? So the standard cubic looks like this. If you have a cubic like this is my standard cubic. And if a, b, c are the roots, the Vieta's relations would look like this. A plus B plus C should be equal to minus P. Similarly, AB plus BC plus CA would be equal to Q. And finally, ABC would be equal to minus R. So actually, that is what we are using here. Notice that A plus B plus C is 0. So we have not put a x square term here. While AB plus BC plus CA is Q, we are calling that capital A and we have put that here, right? So it is easy to convince yourself that this equation is such that small a, small b, and small c are roots of this polynomial, where capital A is given by this and capital B is given by this, right? Now we go to the next screen and we'll look at the symmetric sums that I am talking about. So this is my equation. AB plus BC plus C plus CA equal to capital A. And ABC equal to capital B, right? For each positive integer n, let's define this quantity. Let's define P of n to be a power n plus b power n plus c power n. Why are we defining something like this? Because if you notice in the problem, we had a power 5 plus b power 5 plus c power 5, a cube plus b cube plus c cube. So basically, we have terms like t5, t3, and t2 in the problem, right? So I'm just defining a general quantity like this. Now you can see here, t of 0 is equal to a power 0 plus b power 0 plus c power 0 is equal to 3. And what is t of 1? T of 1 is a plus b plus c is equal to 0. That has been given in the problem. What is t of 2? T of 2 is simply a square plus b square plus c square, which is equal to a plus b plus c whole square minus 2ab minus 2bc minus 2ca. So that becomes t of 2, since a plus b plus c is 0, 0 minus 2 times ab plus bc plus ca, that is called capital A. 0 minus 2 capital A. So minus 2 capital A is my t of 2, right? Now, how do I find out higher powers, right? So here is where symmetric identities by Newton come in handy. So what I will do is I will show you a short proof for that, right? So first I will do the proof and then I'll use the identity, right? So if x cube plus ax minus b equal to 0, and I multiply this equation by both sides with x power n, I will get x power n plus 3 plus a x power n plus 1 minus b x bar n equal to 0, right? This is also a true identity because it follows from the original equation. Now I'll put x is equal to small a, small b, small c in this equation, right? So I'll get what? A power n plus 3 plus a small a power n plus 1 minus b small a power n equal to 0. Similarly, b power n plus 3 plus a b power n plus 1 minus b power n equal to 0. And lastly, c n plus 3 plus a c power n plus 1 minus b c power n equal to 0. If I add these three together, if I add these, what I get is a power n plus 3 plus b power n plus 3 plus c power n plus 3 plus a common a power n plus 1 plus b power n plus 1 plus c power n plus 1 minus b common a power n plus b power n plus c power n equal to 0, right? So I'm simply adding these equations. And now you notice that this is actually t of n plus 3, t of n plus 3 plus capital A into t of n plus 1 minus capital B into t of n equal to 0, right? So this is the symmetric identity which basically connects higher terms like t of n plus 3 and t of n plus 1 to lower terms, right? So I will just rub off this derivation here and we'll work with the final result, right? So I'm going to write here the general result that we have gotten. We got t n plus 3 plus a times t n plus 1 minus b times t of n is equal to 0, right? Now, how do I use this result? So if I put n is equal to 0 here, I will get t3 plus a t1 minus b t0 is equal to 0, right? So that will give me the value of t3 because I know t1 and t0. Notice that I know t1 and t0 here, right? So what is t3? T3 comes out to be b t0 minus a t1 and b t0 is 3. So it is 3 times b minus t1 is 0. So that is 0, tb. So we have gotten t3 is equal to 3b, right? Great. Now we try to find T4. When I put n is equal to 1 in this, I'll get T4 plus A T2 minus B T1 equal to 0. So T4 is equal to B T1 minus A T2. And that comes out to be, what is B T1? That is 0 minus A T2. A T2. T2 is minus 2A. Minus A into minus 2A. So that is 2A square, right? That is my T4. Great. So once I have T4 also, I'll be able to now find T5. How do I do that? I will just put n is equal to 2 in the original relation, right? So n is equal to 2 in this relation. So that will become T5 plus A T3 minus B T2 equal to 0, right? So T5 will be equal to B T2 minus A T3. What is B T2? T2 was equal to minus 2A. So it is becoming minus 2AB. And minus A into T3. T3 was 3B. So minus A into T3 is becoming minus 3AB. So this is minus 5AB. Right? So we have T5 is equal to minus 5AB. T2 is equal to minus 2A. And T3 is equal to 3B. Right? So now the result follows very easily. What we wanted to prove was T5 by 5. What I wanted to prove initially was T5 by 5 is equal to T cube T3 by 3 multiplied by T2 by 2. Now you notice here T5 we have already found. So T5 by 5 is equal to minus AB. And what is T3 by 3? T3 by 3 is equal to 3B by 3 is equal to B. And what is T2 by 2? T2 by 2, T2 is minus 2A. So T2 by 2 is minus A. So when I multiply T3 by 3 and T2 by 2, I'm getting minus AB here. And I'm also getting minus AB from T5 by 5, right? So The problem is solved, but the main idea of the problem is this recursive identity where we connected t of n plus 3 with t of n plus 1 and t of n, right? And we have seen a short proof for that identity as well. It comes by simply multiplying the original equation by x bar n and substituting x is equal to a, b, or c in that, right? Notice that it would have been really annoying to try to find out T5 directly by Vieta's relations. Do not try to find P5 or A power 5 plus B power 5 plus C power 5 by Vieta's relations. It will be super annoying. You should always try to use these symmetric sum recursive relations, right? So hopefully you have learned something from this video. I already have another video on my channel which talks about Newton's symmetric sums in a lot more detail. But I think you should be well served by just learning what we did in this problem and applying it to problems that you might encounter in the future. So I hope you liked the video. And if you like the video, please subscribe to the channel and I'll see you in the next video. There is a lot more content coming your way. So continue watching and learning. See you next time.